Hello everyone, I am Marco Antonio Rodriguez Flores and I will introduce you to our work Latent Geometry and Dynamics of Human Proximity Networks. This is joint work with my advisor, Dr. Frankiscos Papadopoulos. Human proximity networks are time-varying graphs of social interactions in a physical space. They consist of a series of network snapshots, each snapshot representing a time slot where nodes are connected if they are within proximity in the slot. The time-aggregated network representation is also studied. This is a weighted network where nodes are connected if they were within proximity at least once, and the weight of an edge is the total number of snapshots where the connected nodes were in proximity. Real networks can be obtained from the social patterns collaboration. In these networks, the proximity detection between people is up to 1.5 meters, time slots have a duration of 20 seconds, and the total observation periods are a few days, while the networks from the MIT Human Dynamics Lab offer a proximity of up to 10 meters, time slots of 5 minutes, and total observation periods of several months. Human proximity networks are important to study information transfer from person to person, community formation and evolution, and perhaps the most important is to study the spread of contagious diseases, which is particularly relevant today. Here we have the typical characteristics of human proximity networks. We see that the number of nodes is relatively small, the network snapshots are very sparse and fast evolving, whereas the time-aggregated network is dense. The common properties of human proximity networks that are studied include the contact and intercontact duration distributions. These are broad distributions compatible with power laws, with reported exponents bigger or equal than 2 for the contacts and between 1 and 2 for intercontacts. Properties of the time-aggregated network include the weight and strength distributions. But there are also many other properties that are of interest. To model these networks, we propose the force-directed motion model, a model of mobile agents, where agents reside in a latent similarity space, a circle, besides the physical space where they move and interact. Each agent has a similarity coordinate, its angular position on the circle, and the similarity distance between two nodes is their angular distance. The main idea in the model is that the motion of the agents is directed by similarity forces that decrease exponentially with the similarity distance, and also the contact durations decrease exponentially with the similarity distance. Specifically, the agents have the reposition in snapshot t to the next snapshot t plus 1 according to the motion equation on the slide, which combines displacement due to the summation of the forces exerted on the agent by the other agents and a random displacement towards the right direction chosen uniformly at random. Actually, this kind of motion is akin to Langevin dynamics in the large friction limit. Notice that if we set the force magnitude to 0, then the agents perform random walks. But if we set the random displacement magnitude to 0, then their motion is deterministic. The agents pose to interact if within distance d from other agents, and they resume mobility with the probability on the slide, which assumes that the contact duration between the nodes is exponentially distributed. And we can see that the probability is an average over the neighbors in the snapshot. Here we can see the FDM in action in fast motion. On the left we have the similarity space, and the black lines represent the interactions happening in the physical space on the right. It's clear to see a concentration of black lines among the nodes that are closer to each other in similarity space. The FDM reproduces many common properties of human proximity networks, such as contact and intercontact duration distributions, which previous models of mobile agents also reproduce. But what is important here is that the FDM also reproduces complex group dynamics, such as the formation of recurrent components. These are groups of the same people that appear recurrently throughout the network snapshots. On the top right, we have a plot where the blue lines mark every time a recurrent component appears in the real network of the primary school. We can see that they are abundant. But if we assume that the motion of the agents is random, like in previous models, then we see that the recurrent components do not form as abundantly. In contrast, if we introduce force-directed motion, we can reproduce the formation of recurrent components as abundantly as in reality. We can then compare the average number of recurrent components where a node participates as a function of its number of interactions. In the plot, we see a strong agreement between the FDM and reality, but not with random motion. A very interesting result with the FDM is that we observed a connection to the S1 model of traditional complex networks. In the S1 model, nodes have a hidden angular coordinate and a hidden degree proportional to the node's expected degree. The effective distance between two nodes is proportional to their angular distance over the product of their hidden degrees. In the model, nodes connect with the Fermi-Dirac probability, and the temperature parameter between 0 and 1 controls the average clustering coefficient. In synthetic networks generated with the FDM, we have observed a qualitative resemblance between the connection probability per snapshot, the markers in the plots, and the Fermi-Dirac connection probability, which are the blue lines in the plots. We have thoroughly investigated this connection and proposed the dynamic S1 model, which forgoes the motion component and instead assumes that each network snapshot is a realization of the S1 model. In the dynamic S1, nodes have a hidden angle and a hidden degree like in the S1, and we generate snapshots from 1 to tau according to the following steps. At each time step t, snapshot gt starts with n disconnected nodes. Each pair of nodes connects with the Fermi-Dirac connection probability, and at time t plus 1, all edges in snapshot gt are deleted, and we repeat the process to generate snapshot gt plus 1. Here we show a visualization of 5 snapshots generated with the dynamic S1. Nodes are placed on the circles according to their angular coordinates and colored according to the connected component where they belong in the snapshot. The pink lines represent the interactions in the snapshot, and, for example, we see that the yellow component in the first snapshot is a recurrent component in the third. In the dynamic S1, the temperature parameter controls the average degree in the time-aggregated network. And we have also proved that the contact, intercontact, and weight distributions are power laws with exponents 2 plus t, 2 minus t, and 1 plus t, respectively. Dynamic S1 reproduces all main common properties of human proximity networks, but it also reproduces the formation of recurrent components, like the FDM, despite being much more simpler. Here we compare epidemic and rumor spreading between real networks and their synthetic counterparts generated with the dynamic S1 model. For epidemic spreading, we consider the infected susceptible model, where infected nodes infect their neighbors in the snapshot with probability alpha, and infected nodes become susceptible again in each snapshot with probability beta. For rumor spreading, we consider the ignorant spreader-Stifler model, where spreader nodes communicate a rumor with probability alpha to their ignorant neighbors in the snapshot, and spreader nodes become Stiflers and do not spread the rumor anymore with probability beta. In both cases, we observe a similar behavior between the real networks and their synthetic counterparts for the same values of alpha and beta. In epidemic spreading, we consider the prevalence, the proportion of the population that became infected, while in rumor spreading, we consider the size of the rumor, the proportion of the population that became aware of the rumor. In ongoing work, we embed real human proximity networks into the hyperbolic space. After further analysis of the dynamic S1, we have found that we can do this by embedding the time-aggregated network with existing methods for the S1 model. We present an example for the real network of the primary school and show that these embeddings are meaningful and actually useful. For example, community detection. Here we place the nodes in the dish according to their inferred hyperbolic coordinates and color the nodes according to their classroom or if they are a teacher. We see a clear separation of nodes into communities in the hyperbolic space. We can also visualize the spread of the disease. In this case, we color the nodes according to the period when they were infected, and the source of the infection is the node with the red outline. We see that the infection first spreads within the community and then it spreads to adjacent ones. We also found an interesting result that shows that the time slot when a node becomes infected is significantly correlated with the node's hyperbolic distance from the source of the infection. With our work, we want to gain better understanding of spreading dynamics in human proximity networks through the lens of their hidden geometry, and further explore the predictive power of the embeddings in this context. A natural direction to follow is to extend existing embedding methods so that we can update the inferred coordinates as new snapshots become available. And an open problem for dynamic networks in general is to find the stochastic differential equations that dictate the motion of nodes in their hidden geometric spaces. Thank you very much for your attention. Please feel free to grab our papers, code, and datasets.